We are entering now the final stretch, the last packed 2 days with a mix of lectures and research talks. And getting us underway is, again, Georg Bergner, his second lecture on matrix models, holography, and their simulations. Over to you, Georg.
Thank you, David. Yeah, the last time I've told you a little bit about the theoretical background. So I started with this nice membrane theory, which unfortunately led then to the conclusion that these objects would be unstable. And then we left a little bit the solid ground of these theoretical well-defined theories and then went into these conjectures about these connections to M theory and about the general connections to string theory and M theory as a kind of general universal theory that is behind all this kind of string theory formulations. And then also towards the gauge gravity duality, which is another set of applications or a different regime where you can investigate this relation to this matrix models. And now, after we went through all of these things, we can now go back to, so to say, well-defined physical questions, because we now have this matrix models at hand and can investigate their properties. And this is what basically was my conclusion here about this matrix model, that it's still not, has some flaws concerning the theoretical applications and the definition of M theory, but at least it's something that you can investigate. And also concerning the interaction of these numerical applications and the theoretical foundations or the theoretical foundation developments, it's always nice that this forces people to really pin down things, to formulate things in such a way that these get measurable questions that you can investigate. And this leads to a better formulation also of the theories, I think. So in this lecture, I will now spend some more time on how to simulate these theories on the lattice. So normally when I talk about lattice supersymmetry, I would have to cover a lot of things about four-dimensional theories where the formulation of lattice supersymmetry gets much more complicated. But fortunately, David has covered this, and therefore I can really focus here on the supersymmetric quantum mechanics and then these supersymmetric matrix models, where things are simple and easy to understand, and therefore also a little bit more pedagogical to so people with who don't have much background in lattice field theory can understand these basic problems. So I went already through these possible applications, which are clear from the motivations that I gave. And then I ended last lecture with this basic statement, which is also a summary of what David has covered. Basically that you have only the possibility to realize a symmetry on the lattice either explicitly, you can have a Ginzburg-Wilson relation realization, or accidentally. And unfortunately for supersymmetry, these two first points are not possible. So concerning this Ginzburg-Wilson, this relation, why this is not, why no solution has been found so far for this Ginzburg-Wilson relation, this might be a little bit more obscure, but I can maybe write just the zeroth order problem that you have in such a Ginzburg-Wilson formulation. And this is if you just go do a blocking step, even in the continuum, and you want to define a derivative operator that then acts on some kind of averaged fields. So in this blocking kind of definition, you would associate a lattice field with some kind of blocked continuum field. So you have some function that averages the continuum field around a certain lattice point. And this defines then your average field that you want to use to associate it to a lattice field. And now what you want to do is to translate somehow now the translational invariance already from this original fields to some lattice definition. So you wouldn't need something that some lattice derivative operator that somehow equals or is at least in a certain way a representation of your derivative operator that you have in the continuum. And already these kind of formulations that you need to get some meaningful definition in this kind of Ginzburg-Wilson sense, which means a kind of randomization group step, is very complicated and in general leads to some non-local definition of lattice derivative operators. And this is a basic problem why there is no, why basically no solutions for this Ginzburg-Wilson relation or a realization of Ginzburg-Wilson symmetry in the Ginzburg-Wilson sense of supersymmetry has been found. Also not, of course, of the translational invariance. And therefore, we are left only with these two other cases, which are basically the same. You have to look at all possible mixings and then add to the action some symmetry breaking operators and tune their coefficients in such a way that they compensate the breaking that you have introduced by formulating the theory on the lattice. And as I said, this general problem has led to many non-standard lattice approaches, such as the twisted formulations that David has considered. So to put this in a more simple way and to understand it in a more simple way, one can just look at supersymmetric quantum mechanics, the most simple supersymmetric lattice models. So you have an off-shell formulation where you have these auxiliary fields F here, otherwise you have the scalar fields and fermion fields here, and then you have a kind of superpotential which generates you fermionic and bosonic mass terms as well as the interactions here, Yukawa interactions, and then if you integrate out the auxiliary field and get to the on-shell action, then all kind of other interaction vertices are generated also in the bosonic sector. So the off-shell, in the off-shell form, you have a nice linear form of this supersymmetry transformation. In the on-shell form, you get this nonlinear term here. And in this formulation of supersymmetric quantum mechanics, it's basically an n equals 2, so you have two different supersymmetry transformations. And if you do the transformation, you will observe, which is the case for all kind of realizations of supersymmetry, that you get only an invariance of the action up to a total derivative term. And this, but in order to see this, to get this invariance, you also need to apply the Leibniz rule on the lattice, which solves here these derivatives that appear here. Now you can go through all the steps that you have learned in Anna's lectures and just put it in a standard way on the lattice, which means that you introduce forward or backward derivative operators for this boson field. This means just a difference in forward or backward direction that you calculate here. And then in case of the fermions, Anna probably has covered this in her lectures. You first, if you want to have the symmetries as in the continuum, you need something that is called usually the symmetric derivative, but it's actually an antisymmetric operator. So these are differences, of the point in forward and backward direction divided by 2. And then you will find this will give you the correct hermeticity properties that you need for this fermion action, but you see that this naive implementation leads to doubling of the fermion modes. And you had to add a Wilson term here. In one dimension, this is actually quite simple because it brings you back to a forward or backward derivative depending on the sign of this additional Wilson parameter R here. Now the thing is, if you just do this standard lattice form implementation and simulate it on the lattice, you will see that it doesn't lead to a supersymmetric continuum limit. So if you go to the continuum limit, you will see that you have a huge difference between the bosonic and fermionic mass terms. So, but this can actually be understood in terms of lattice perturbation theory. Normally would think that there are no divergences here in this quantum mechanical problem, but actually one can see that in an explicit calculation that you have in the fermion loops that the boson propagator gets, you get an additional contribution that comes from the Wilson mass of the fermions, which, as you know, diverges in the continuum limit. And this gives you a finite contributions just due to the fact that you have in this loop diagram this additional mass contribution. And so after you solve the integrals, actually it's a finite additional contribution that you get from this term, but it will spoil this fermion bosonic mass degeneracy. Now, the good thing is that since this is calculable, you can, it's only one diagram that you need to consider, and the other supersymmetry breaking terms vanish in the continuum limit. And this is something that generalizes to all kind of super-normalizable theories. If there's only a finite number of diagrams that lead to this violation in the continuum limit, then, which is true for these kind of theories, then you know how to compensate this. So you can add a counter term to the action and tune the coefficient accordingly, and this leads then to the correct continuum limit. And so in this kind of approach, in this tuning approach in supersymmetric quantum mechanics, you would add an additional term. You can compute this explicitly, and it has a finite coefficient that you can also determine. So it's just an additional term that you need to add here to the action. There are actually also other ways that you can deduce from this diagrammatic expansions that you can use to get the correct continuum limit. And one very obvious way is that you add the Wilson mass term in a consistent way to the superpotential. So in this way, also the bosonic mass would appear here in the superpotential. It would just start with m times phi, and then some higher interaction terms would appear here. So in the same way, you would add here this Wilson mass term in a consistent way. And this would also lead to a supersymmetric continuum limit. And another way to formulate this is if you just formulate this in terms of a square here of this operator. And this second formulation, if you just look back at our definitions of the supersymmetry transformation, and calculate the transformation, you will observe that this last formulation, which is the same as this one up here, up to a term that basically is a surface term in the continuum, then this kind of formulation has an intact supersymmetry on the lattice. So one of the two supersymmetries is preserved for this kind of formulation. So for the fermion terms, of course, they always stay the same in this kind of reformulations of the lattice theory. And this can also be expressed now, since you have an exact supersymmetry, you can express this in terms of an alternative formulation where you introduce here an auxiliary field. And this auxiliary field appears then also in the transformation of the supercharge. And you will observe that you get in this way a nilpotent, so the square of this first supercharge here is 0. And therefore, you can formulate this complete action then in this kind of Q-exact form.
Can I ask a question?
Yeah.
So in previous slide, you talked about boson doubling. So is that for like countering the fermion doubling?
Where?
So there is written like.
Okay. Yeah. So yeah, this was just to mention that if you don't add here this this bosonic Wilson mass term, and you just add here a symmetric derivative as you would for the fermions. In the fermion action, you have to use this naive lattice derivative because you want to have the correct hermiticity properties, but you can introduce this also for the bosons, but this leads actually to a boson doubling problem. So you do basically in this kind of formulation, you do the same things in the bosonic and the fermionic sector, which is, so to say, understandable. You use the same derivative operators, and then you generate the same doubling in boson and fermion sector, and then you add this additional mass term, the Wilson mass, then also for bosons and fermions.
So that Wilson mass counters the doubling.
Yeah, this then counteracts. So basically the same things happening in the bosonic and fermionic sector this way. The disadvantage is, of course, that also the lattice artifacts, one knows that the Wilson term leads to larger lattice artifacts in the in this fermion action that you usually have for the boson actions, that you actually introduce in this way larger lattice artifacts also for the bosons. Any other question? Okay.
Thank you.
Domain wall. If I understand what you're doing here, you're forcing the operator for the boson to be the square of the Dirac operator. Right?
Yeah.
Isn't that what this amounts to? Or am I wrong?
Yes, I mean, it's a little bit. So this in this mass term here, if you square this complete expression here, generates also additional bosonic vertices. So in the free theory, you are right. This
in the free theory, that's what you're doing.
In the free theory, that
but with the interaction, then you have to do it in this way.
And the interactions, but in the interacting case, it's more complicated because you generate actually Wilson mass dependent vertices in the bosonic.
I mean, this is probably naive because people thought about it, but there is a local higher dimensional Dirac term in domain wall, right? So could you try to follow this and try to make the boson be the square of that? I'm trying to, at least at the free level, use Ginzburg-Wilson and inherit the Ginzburg-Wilson from the Dirac to the boson, which I'm trying to follow this sort of thing.
So I think, so actually they are higher in this one-dimensional case. You don't have to talk about this overlap or domain wall because these are actually, in this case, rather trivial constructions. But in a higher dimension, this hasn't been, in fact, tried to somehow split from an overlap operator.
Overlap and domain wall are almost the same, but they're different in a very important way. The domain wall is local in an extra dimension.
Yeah.
Okay, so I mean, it gives you a simpler way to get to the overlap, and it's exactly the same as the extra dimension goes to infinity. So, I mean, while they're technically the same in this limit, they're algorithmically quite different until you reach that limit, okay?
Yeah.
So I wouldn't lump the tricks that you might play entirely under the overlap formalism.
Yeah.
I think the domain well one is much more physical. Anyway, just comment. Okay.
Yeah, we can discuss it afterwards. Actually, in higher dimensions, similar things have been tried with overlap, but I think this led to some non-local lattice theories.
It's always non-local when you compress it to the lower dimension, but it's local in the higher dimension in domain well.
Mhm.
It's a special approximation to make that true using overlap. So
Okay.
I would advise people to consider these two as somewhat independent avenues, even though there's one limit in which they become the same, but that's a limit, right?
Yeah, it could be that with this kind of domain wall, it could be formulated in a simpler, maybe local way. Maybe we can discuss it afterwards, because it's more complicated, because it leads to this in higher dimensions. There is a different structure, and
We're all used to adding an extra dimension.
yeah. Yeah, but okay, yeah. Back to this rather simple models now. Let's stay first in one dimension. So the this kind of symmetry formulation lets you formulate the theory as a Q-exact form. So as a Q variation of this term here, and then you know that if you would act then again with another supercharge on it, that this would lead to of course, to a symmetric action. And for this also shows very explicitly that you don't need this kind of additional terms that are generated due to this Leibniz rule on the lattice, and this additional surface terms that are always a problem. So this is in fact the lower dimensional counterpart of the twisted formulation that David has talked about. In higher dimension, of course, the reason it becomes more complicated is because you need also to ensure that somehow this supercharge that is, which squares to zero, up to gauge transformation at least, that this is a scalar, otherwise you cannot fulfill this. Now, this is a way to have at least one of the two supersymmetries on the lattice. Now you can wonder whether you can get the complete supersymmetry on the lattice. So we have seen that the Wilson term generates some problems. So let's go to a non-local lattice derivative operator, because you know from probably it has been covered in Anna's talks, this Niishimura theorem, which tells you that if you don't add the Wilson terms and break chirosymmetry, then you would need some kind of non-local lattice derivative operator. So you can add this derivative operator, and you can even show that these kind of derivative operators lead in this one-dimensional case to the correct continuum limit. So you don't have the problems that you have in higher dimensions with these kind of operators, which in higher dimension lead to a non-local and even non-Lorentz invariant continuum theory. But and you can then also introduce a derivative operator in the transformations and in the action, which is antisymmetric, and therefore you can easily translate then with this kind of derivative operator the continuum transformations on the lattice. And this antisymmetry also already ensures that any quadratic action would be invariant, because the terms that I've written in the beginning, which are generated due to this symmetry transformation, would just be a sum of these two terms, and these, just by antisymmetry, these vanish. But if you go to the interacting case, this is still not enough. So in this case, what you get is that you have to fulfill basically the Leibniz rule on the lattice. So I'm always assuming that a summation here over these lattice indices. And with this kind of derivative operator, you can then transform the derivative. So if you have just this, the next thing would be just in the superpotential, you would have in the derivative of the superpotential, you would just have a squared term. And if you go back to these terms that I've shown in the beginning, then you would, then you can transform this derivative operator from the fermion to this boson squared. And then you would, this would have to be equal to this term in order to make up the supersymmetric invariant action and to have a vanishing variation of the action. And this is basically what David already mentioned, this violation of this Leibniz rule that you need to implement on the lattice. If you now transfer the Leibniz rule into the momentum space, then you see that you get this kind of representation in the momentum space. And now you might wonder what kind of operators you can choose to fulfill this, this lattice discretization. And of course, if you just look at it, of course, it would just be that it follows the same dispersion relation as in the continuum, and that the operator applied to the momentum is just the momentum itself. Then you would get that this part here is fulfilled up to the fact that on the lattice, since you have introduced a lattice cutoff, this would also always have to be periodically continued. So you have a periodicity if the momentum leaves the Brion zone, that it enters, so to say, from the other side. So you have a periodicity in the momentum space that you have to fulfill for all kind of lattice operators that you can define on the lattice. And therefore, this momentum space relation of the Leibniz rule cannot be fulfilled for momenta that if the sum of the two momenta leaves the first Brion zone, and you have, in addition, to modify the product rule on the lattice in such a way that it projects out these high momentum components. So if you have a square of two fields on the lattice, then in momentum space, you get the sum of these momenta, and this can be higher than the lattice cutoff. And this you need to explicitly cut away in order to have the Leibniz rule fulfilled on the lattice. So what you need for this kind of implementations of the complete supersymmetry on the lattice is a kind of non-local derivative operator that implements the continuum dispersion relation. And in addition, you need something to project these in the product of two of these of the fields projects out the higher momentum modes. And this can be done, and one can really simulate with these kind of theories. They are highly non-local, and so I've done these simulations, but I think this is also related to what Masanori has done, and also other approaches which basically start from the beginning in the momentum space. And in that way, you can preserve all of the supersymmetries in this lattice action, even at a finite lattice spacing. Yeah. And in order to illustrate this, here are some supersymmetric Ward identities. So you see here that you can either have a breaking of both of the supersymmetries and fine-tune the problem in order that this breaking becomes smaller if the continuum limit is achieved. You can have the case here in lattice simulations where you have preserved one of the supersymmetries on the lattice, and you can preserve both of the supersymmetries on the lattice. So all of these approaches have advantages and disadvantages. This is the most simple approach. This here has a better realization of supersymmetries on the lattice, but usually breaks other properties of the lattice structure. For example, reflection positivity is in these cases not, in this simple case, not violated. And then you have the complete realization, but this breaks then even the locality on the lattice. Okay, are there questions so far? Okay, then I just summarize what basically to learn from these approaches, also about the more general lattice implementation. Usually, if we think about lattice theories, one has a certain number of requirements that one wants to achieve with the lattice implementation. One wants to approach the correct naive continuum limit, of course. One wants to remove all kind of doublers. Then you have the usually implemented reflection positivity, which is just due to the axioms of quantum field theory that you want to implement this. Then you want to implement locality, and on the lattice, this usually means that you can have interactions with arbitrary far away lattice points in your lattice action, but the interaction strength should decay at least exponentially. This is what is meant by locality. Then you want to keep the hypercubic symmetry usually, and usually you want also to keep gauge symmetry. This leads to very difficult consequences if you don't have it. And you want to avoid any kind of sign problems because you want to have an interpretation in terms of some measure in a probabilistic sampling then. But unfortunately, since due to all of these problems with formulating supersymmetry on the lattice, for many of the non-standard lattice approaches that are usually implemented, these points, except the first two ones, can not be guaranteed. And this, of course, one always have to keep in mind, and one has to check carefully that the correct continuum limit is approached. And also, as another warning, even if you have checked that operators shouldn't, if you look at your perturbative studies, that all these kind of additional operators that you add to the lattice action in order to improve supersymmetry, even if you know that these are irrelevant and should vanish in the continuum limit, it doesn't mean that they are really irrelevant in your simulations. This is here, I think, the simplest example, which is a two-dimensional West-Zumino model, where you can also add these kind of improvements terms that I've mentioned in the beginning to have one exact supersymmetry on the lattice. But what you observe is if you go to larger couplings in this lattice investigation, that at a certain coupling you enter phases where this additional term that you add to the action becomes really large. And whereas at small couplings it's as expected really an irrelevant additional term, there are additional phases that you have basically added to the system then just by adding this improvement term. So this means that you have to understand also the phase structure that you have for these kind of theories. If you have something that extrapolates nicely to the continuum limit, you also have to check that you are in a phase that is really connected to the physics that you want. But of course, I mean, for the especially for this twisted formulation, there's a lot of checks and additional terms and also investigations that have confirmed that that the approaches work if they are done in a proper way. So now I want to go to the Bfss model and discuss the different approaches that have been used there based on what I've explained a little bit in terms of these very simple supersymmetric quantum mechanics. And I just want to say here in the beginning that there have been various different approaches, and in some cases they have been just tried once and to just do one investigation, and then later on they have not been followed anymore. And unfortunately, it's not always clear which one of the approaches is better than the other. And what is really lacking is a comparison of the different approaches. So if the difference, if you want to go to the gauged case here, is actually quite simple. As usual, you add these parallel transports for the gauge fields that live on the links of the lattice, and then you can formulate in a gauge invariant way this derivative operators, which have for the forward and backward derivative, and these are formulated in this way because the fields are in the adjoint representation on the lattice. It's actually similar to what you probably have seen in Anna's talks for the fermion operator for the fermions, but these are in the fundamental representation. This makes the only difference here, basically. In the same way, you can always go also to larger differences just by using this parallel transports over more than one lattice spacing. Now you can introduce this in your and apply this in a standard way as we have done for the West-Sumino models, and introduce here a forward derivative. And then it turns out, due to this Majorana-Weil structure, that you will have a little bit different structure here for these Dirac terms usually. So you have the forward and backward derivative that appears here. But this is just due to the fact that some kind of anti-symmetry property should be kept for the Wilson term that you add here in terms of the Majorana fermions. So you would have some in this original formulation. You would have here a kind of charge conjugation matrix if you replace this psi bar here with this transposed operator. And this leads to this structure where you have the symmetric, where you have the forward and backward derivative operator here. But this is all, so to say, the standard way that you would implement this. And one can show that even though this is a standard way, and you know it doesn't work in the supersymmetric quantum mechanics case, that for this gauge theories, for this BFSS, it leads to the correct continuum limit. And basically, the reason for this is that these Yukawa couplings that would generate, basically, that would couple the boson fields to the fermions, that these have an antisymmetric structure, and this leads to a vanishing of this of the loops that you would get in the perturbative expansion that spoil the continuum limit. So in fact, in a way, this is an approach where this fine-tuning that you have for the West-Sumino model vanishes. And this has been used quite a lot in the lattice simulations. So in these earliest simulations by Simon Catterall and Toby Wiseman, and then also in simulations of the BMN model.
In that lattice action, it's me. Could you remind me what the R is in the prefactor?
Okay, so this is just to go to dimensionless units. If you sometimes here a lattice spacing is introduced, so you want this R over L generates here just a dimensionless parameter for the.
So it's like the dimensionful extent of the system, and L is the number of points.
Yeah. So and in addition, you can use the gauge degrees of freedom in this one-dimensional case are quite simple to handle, because you can either gauge all of the links to the same value, which is used in some of the simulations, or you can use the gauge fixing that you get only one of these links and set all others to the identity. This is what's usually used in the simulations. In several other simulations, an additional step is done, which is done also to diagonalize this first link. And this gauge fixing generates an additional term that you have to add to the action just because of this, an additional ghost term that you would have to add to the action in order to compensate for this kind of gauge fixing. And this is also used in many of the simulations. Then if you consider the Wilson term, there are actually different ways to add this. One can decompose it into this symmetric derivative, and then you can add this Wilson term in several different ways. One standard way would be to have this, actually it's C times, so to have here a kind of this antisymmetry in this additional part, such that you get here the forward and backward derivative. But actually by Denjo and his collaborators, there have also been other possibilities where you add this in such a way that you have something that leads to an anti-commutation with these additional terms that you have in case of the BMN model. And they've shown that this leads to an improvement if you compare then the dispersion relation of the squared of the Dirac operator with the dispersion relation that you would have for the boson operator. So these are properties, since this gamma structure is in this one-dimensional case is to a large extent just an internal symmetry. You can play a lot with this kind of additional freedom, and then you can adjust to have a more optimized way to add the Wilson term. Then you can also consider different ways of improvement for this standard action, and this has been done in the very recent, very precise investigations of the BFSS. So you would add higher terms in the lattice spacing to compensate the breaking, the remaining breaking that you have from the simplest implementation. And if you omit now the gauge fields and just look at the forward and backward and at the symmetric derivative, you can just derive this in momentum space by adding higher orders corrections to this approximation of the continuum dispersion relation. And in addition, you can use a similar way also for the to improve the Wilson term, such that it only generates higher orders in the momentum. In another paper which have where lots of investigations of the Bfss model has been done, the improvement has been done in a different way by insisting on that you keep the similar form as you would have in the standard implementation, by having only a derivative operator that connects in forward or in backward direction. And by implementing these kind of improvements for the derivative operators, you are of course much more restricted than if you would have a different improvement that you would add for the Wilson term and for the symmetric derivative operator that you have in the lattice action. But what they have shown in this paper is that it's really important to add this kind of additional improvement terms. So if you look here at this continuum extrapolation at not too low temperatures, then you see that you have to go to quite large lattice sizes. You always have to remember that we want to go to the large n limit in these kind of theories. And therefore, you cannot simulate too large lattices. And you have quite a steep extrapolation to the continuum limit. Whereas if you have this improved action, then you are much closer and get much more precise and consistent continuum extrapolation. Later on, Denjo and collaborators have considered more carefully the possible improvement terms that should be considered for these kind of theories. And they have added an improvement of the derivative operator, as I explained basically here, which does not insist on this forward and backward property. And therefore, they were able to improve the Wilson term independently, and also the bosonic term with independent coefficients. And you can see from the dispersion relation, so the blue one is what you would have in the continuum. This yellowish one is what you get with with the standard implementation. And the green one is what they have used. And in this Berkowitz et al. Paper, you see this red one. And what you can see from this investigation is that this improvement basically only improves the Wilson term, whereas for the standard derivative operator, it doesn't lead to much improvements. And whereas this improvement that has been suggested by Denjo leads to much more consistent improvement here. So probably this is a better way, but one really has to compare it in the relevant interaction range to make a concrete statement about this. Now, one can also keep part of the supersymmetry intact for this kind of low dimensional Bfss model. And this has first been done. So first investigations in that direction were done actually with a simpler model, which is only the 4 supercharged model, basically n equals 1 in 4 dimensions reduced to 1 dimension. And this has been done by Simon Catterall and Toby Wiseman. And what they found is basically that they have derived this from a reduction of their twisted theory in 2 dimensions. And it, of course, leads to improvement of the supersymmetric Watt identities, which are now exactly conserved. But on the other hand, they've seen an increased stability problem with respect to the flat directions. And it's from their study, it appeared that both of actions converge to the same continuum limit, but the one with the twisted formulation, so this intact supersymmetry, is much more challenging and numerically intense. Then there was another formulation which is more involved. Even this is formulated by Zugino and Daisuke and collaborators have simulated this. This is also a kind of twisted formulation, but it leads to a quite involved lattice formulation. And the most non-trivial part appears if you go to the lattice, because it adds a contribution to the variation of the fermion field where bilinear of the fermions appears. This is just as in a lattice modification of the continuum supersymmetries. And this generates a 4 Fermi term in this kind of theories, which makes it really complicated. So you have to introduce via Hubbard-Stratonovich an additional scalar auxiliary field to simulate these theories. What is interesting is that in this Berkowitz et al. Paper, they compared this formulation, the results from this formulation, also to their standard formulation, and it shows that they seem to be improved with respect to this, to the standard formulation. So it might be that this, despite the fact that this is a very complicated formulation, that this leads to a better lattice formulation and is better for simulations. And there are also other formulations with exact supersymmetry that actually have never been really tried in simulations, which are this formulation by Kaplan and Insal. The first lattice simulations of the BFSS were actually done in an approach that was called non-lattice by the authors of these papers, but it's actually a lattice formulation which introduces a kind of momentum cutoff. And this reminds us to this exact supersymmetric formulation that you have in supersymmetric quantum mechanics. The difference is, of course, that if you introduce a momentum cutoff in a gauge theory, this leads to has more consequences. And of course, since supersymmetry is also tied here to the gauge symmetries, that you cannot have then the intact supersymmetry on the lattice. So you have to go, in order to formulate this, you have to go explicitly to the static diagonal gauge. And in this static diagonal gauge, it's actually a very simple modification of this original formulation, because it just means that you have to shift your momenta by these phases that you get in this from these diagonal entries of the link field that you have introduced. So this is only the bosonic part, but the fermionic part is actually similar. And actually, there have been quite good results obtained with this, even though, even at rather small cutoffs that have been considered in these cases. But as I said, here as well, a really detailed comparison to other approaches is not present. Okay, the last part, I will just tell you how to get, if you have a lattice formulation, then to the concrete simulations. But I will do this only in a few slides, because this has been mentioned often before and maybe also covered in the other lectures. Okay, so so what you have to do usually, so in the BFSS model, if you integrate out the fermions, you are not led to determinant, but instead, because of this Majorana while conditions in the original 10-dimensional theory, you will be led to a Pfaffian of the matrix. This can be formulated as a square of the determinant up to a phase factor, and now you can square this in addition, and you get up to a phase factor. And this is then expressed as a bosonic integral of so-called pseudo-fermion fields. This is the way fermions are usually implemented also in QCD on the lattice. And then you can look at the usual lattice gauge theory textbooks, and they will tell you that in order to implement this here, you would have to implement an Rhmc algorithm. Basically, you can, there are a lot of algorithms that you can use if you have a theory that connects only nearest neighbor interactions or only a short distance of interactions, and therefore is easy to update locally. But since you have here this complicated structure with the inverse of the matrices, therefore you need something that acts more globally on the fields. And this is done within a molecular dynamics in an additional fictitious time. And this is what is called here the Hmc algorithm. In this Hmc algorithm, one has to deal, of course, with this matrix, this fraction here, a fractional function. So this function of the matrix, and this is usually approximated in terms of a rational function. And the terms that appear in this rational approximation, they are approximated because you have inverses of this matrix that appears here. These are solved by using iterative solvers. So this is a basic idea of this in a very short way of this Rhmc algorithms. And usually these iterative solvers are the real bottlenecks. Yeah.
I have a question. X to minus 1/4 has a problem near x equal to 0. So do they pade this kind of rational function? Don't you need to know something about?
Yes, you need to know something about the spectrum, and it's always I thought it was covered in already.
No, that was not covered, but
Okay.
I'm trying to understand
Sorry.
the precise way in which
thought
people do this.
that since we had something about lattice field, I thought in Anna's lectures.
No, this was not covered.
Okay.
I'm trying to understand how people do this X to minus 1/4.
What you have to do is you have to assume somehow that the spectrum of your matrix is somehow bounded.
But also lower bound, right?
The lower bound, yeah.
Yes.
Yeah.
And upper.
Yes, the upper bound is usually not such a problem,
Right.
but I mean, it can also be for this, if you have the flat directions, then you can also have a problem with that, but usually the lower bound is a real problem, and then you have some discretization,
Okay.
some errors that you generate.
So
And-
are they of x to minus 1/4?
Sorry?
I'm trying to do how they do the rational approximation.
You use what is called the Rhmc algorithm to optimize a rational function in a certain range. So you give a certain range, you assume that your matrix eigenvalues stay within this range, then you use the Rhmc algorithm to generate a rational function that approximates this function here in this range. And then, so it optimizes just, you give a certain order and it optimizes the difference. And then what you do is in your simulation, you monitor the lowest eigenmodes and you hope that it stays outside this range. Otherwise, you have to do what is called reweighting because, so to compensate basically for the error that you have done.
Thank you.
Yeah, there are actually other ways. So the Rhmc algorithm was developed. And before there were also polynomial approximation, which do this in a simpler way, but the idea there is the same. You always have to approximate the function in a certain range, and the rational approximation is in some respects better than any polynomial approximation that you can choose. Okay, and yeah, as I said, most of the time is spent basically in doing this kind of rational approximation in the simulations. And therefore, also, if you just reduce the model to the pure bosonic part, it becomes a lot easier to simulate. So, yeah. And just to compare it to the usual lattice QCD simulations, we are here in a slightly different regime. So yeah.
Can I just ask one? There's one other trick that we use, which I think was due to Simon's and his group. There's one other trick that we use, which is due to Simon and his group. I believe it's Fourier acceleration.
Yeah.
Do you want to make any comment on that, or do you think it's just a waste of computer time?
There are a lot of strategies, in fact, like that, but I would rather focus on maybe other points that can be imported from the simulations of lattice QCD. So there are other, for example, the integrators that have been used there, and all these kind of details. I would check. I think the simulations here are such that you always need to have a look at what is done in lattice QCD to also do these kind of improvements, because these are really improvements of this Rhmc algorithm. Usually,
prove this is huge in lattice gauge theory. Fourier acceleration has generally not given them much improvement. Yeah, one of the things, you have to introduce momentum modes conjugate to all your other variables, right?
Yeah,
so,
you have.
So, I mean, you could also introduce a different quadratic term for the momentum term. That seems to be very important. But the other thing, I'm not sure if it would work here, is that you can introduce more pseudo-fermions.
Yes.
And that gives a lot of alternatives, which I suspect would be
I mean,
the first thing to do, I think.
Yes, you can use determinant breakup.
Yeah,
and
that's right.
And then also you can use all these kind of things like the Hasenbusch trick and all these kind of things. But unfortunately, this has not been implemented here usually, just because people were focused on just getting results and not optimizing it completely.
I mean, everybody would have their guess, but I would say breaking it up into terms, and then what you find is that different terms can use stiff modes need fine step sizes and soft modes. So since it's only one dimension, stiff and soft is really probably easy to separate.
Yeah.
So I think that would be good. The other thing you find out is that you can use very sloppy inversions, because at the end of the day, you're going to do a correction. So you don't need high precision. So I think that space is very rich in improvements.
I completely agree. And I could tell number of improvements that could be done based on the experience that people have with lattice QCD. The only question is, of course, how much for these models you want to improve, or whether you just want to get as quickly as possible to the results. I just want to tell that there are some differences to lattice QCD simulation, and this is that we usually want to take here the large N and the large L. L here in this case means just the lattice point. So it's in this case, if you fix the temperature, a kind of continuum limit that you want to reach. And therefore, the problem is a little bit more dense than for the lattice QCD simulations, where you have basically a lot of space-time points, but then and each lattice and each of the space-time points you have only small matrices. So this generates a rather sparse problem, with also much less communication that you have to use if you want to apply, for example, a Dirac operator. And therefore, these problems don't scale so well as lattice gauge theory. And also some kind of inversion algorithms or some things that have been applied there for these sparse matrices that are used there don't translate so well probably to this matrix models. One way out here is, of course, that you use, which is used in some codes, also a parallelism of the matrix entries. So you, from your original n by n matrix that you have, you generate small blocks and you parallelize this over your computer cluster by splitting the matrices on different processors. And but as I said, this is not the same scaling that you would have if you just parallelize in the dimensions, in the extent of the lattice. But codes are now available. There is, as I said, much room for improvement, but there are also CPU and GPU codes now available for these kind of BFSS studies. A short comment on the sign problem, because we have seen here that you have to factor out this additional phase factor here in order to have a meaningful simulation. This has to be handled in general by a reweighting. In the BFSS and BMN models, this most likely is not a relevant problem. So the studies here is, for example, one of these simulation of BFSS model, which just investigates the cosine. You can show that you can reduce this complex sign problem rather to also to a real sign problem that is a basic origin for these problems. And this cosine here stays basically close to the identity, and therefore you, in the range of temperatures that are interesting, I mean, we don't know what's really happening if you go to very, very low temperatures, you don't expect much of a sign problem. Otherwise, you would have to do it via reweighting, which is by just adding this phase factor to the observable, and then you have to divide it by this additional factor here, because it, of course, appears also in the measure. There's been one argument that in this Berkowitz paper that tries to argue that the sign problem might not be relevant even if you have sign fluctuation, and this is if you can, if these fluctuations are not correlated with your observable, and you can divide it in this way. But this would mean that then this PQ means phase quenched, so this is a usual simulation. And if you can divide this out, then you would see that your observable here would be just the observable in the phase quenched regime. I'm not sure whether I completely agree with this argument, because you can still have a very small expectation value here. And if you don't have a complete decorrelation, then this leads to a 0 over 0 in this expressions here. So these things become unstable in this case. So I don't know whether this completely works out here in this case. Okay, and then one has, of course, also the problem of the flat direction that one has to deal with. This was nicely summarized actually already in this paper by Simon and Toby. And you see here some results of the simulations at 2 different temperatures. And you see, and what they observed is that at lower temperatures, this is one of the scalar expectation values of this that you get here, that you have at a certain point at a higher temperature this, and you enter, the simulation enters this flat direction, and you have a divergence. Basically, it goes off in this flat direction. And at lower temperatures, this happens even more frequently. So you don't even see this kind of metastability region here. The problem with this problem is, with these investigations of this instability, is that it's a combination of a physical effect. We know that this brain is unstable. also with a discretization effect, because you have the Wilson term and additional terms that that are lattice artifacts that are into play. Then you have finite n contributions which modify. So in the large n limit, it's expected that's more unlikely to hit one of these flat directions. That's just by the entropy that you have and the larger degrees of freedom that you have in the system. But in addition, there are also algorithmic effects. That means whether you hit or not or sample this flat direction depends also on the algorithm. This makes it a very difficult problem to handle. There are usually several strategies that have been used in different simulations. So one is to simulate in a metastable regime, just to cut the simulation basically here and then investigate only this part here. And then and do the averages from this ensemble. And the other possibility is to set an explicit constraint. So when the scalar expectation value hits a certain value, that's then reflected. And therefore you stay somehow in a regime where you only have a small scalar expectation value. And other possibilities is that you add an explicit mass term, which is slightly more controlled, and then you extrapolate to the limit where the mass term vanishes. And of course, alternatively, you can also to approach the BFSS limit from the BMN limit, which has the advantage that you have part of the, so in a way, as the properties of supersymmetry kept in the model, despite the fact that you add something that acts similar to a mass term. The disadvantage of this last approach is, of course, that you have several vacua and that you can still tunnel between these different vacua. And so you have some remnant of this flat direction problem even in the BMN model. This one has also to keep in mind if one compares different results for the from the simulations, because it might also affect what kind of lattice artifacts appear in the simulations and how well controlled the continuum limit is, how the strategy is to handle these flat directions. So to summarize these different approaches, I've shown a number of very different approaches that have been suggested, and even more have been suggested than actually implemented. But what's really missing is a comparison of the improvements and the costs, and this is especially important if we now want to deal with low temperature, precise large N extrapolation of the Bfss model. As we have already discussed, some further improvements are of course possible if one looks at the recent developments in lattice QCD. And the numerical problems, they are in some respects different, but one can learn also then from other studies. For example, in this, as Tony mentioned, this twisted Iguchi-Kawai models, there are really large matrices that are considered there. And maybe one can learn also something on how to improve the algorithms here. Okay, I think I close with it.
We've had a few questions going along, but are there any more before we take them?
Yes, so may I ask questions?
Yeah.
So I'm Takahiro Azuma, participating from Zoom, and in the covariant derivative of BFSS, so I wonder how we can formulate the central difference instead of the forward and backward ones.
In which model?
In the BFSS, the covariant derivative of the Bfss model.
Yeah.
So how can we formulate the central difference of the covariant derivative?
This is the symmetric derivative?
Yes.
Or? Yeah,
Yes.
I mean, I've summarized this here in a very short way. So the symmetric derivative is just if you sum them up, then this term in the middle disappears, and then you just, it's as the ungauged symmetric derivative, but just with a gauge covariant shifts in forward and backward direction that appear there.
So the xt is cancelled here. In the sum, when we take sum, xt is cancelled.
Yeah, the xt is cancelled. That's correct. And then you can also have, I mean, you can also formulate in a similar way the Laplacian, which means you have the local term, and then with opposite sign the terms in forward and backward direction, as you would have in the usual lattice Laplacian, the simplest form of the lattice Laplacian.
In simulating the BFS, is there the advantage in taking ds here instead of d plus or d minus?
Okay, this was maybe a little bit quick. Here, this should be d plus and d minus. I just splitted this in the symmetric part and the Wilson term here.
Yes.
So this is, in fact, if you add these two components up, you would get d plus and d minus here. So these two components together yield d plus and d minus. Just if you would, as done in this paper, add a different gamma structure here, this would be different. But you can also show that you can remove the doublers also in this other way. This has been shown in this paper.
Yes.
So you have some freedom, and still you are able to remove the doublers.
Thank you very much.
Yeah, and yeah, I mean, I can add here that, of course, here you would also always need a kind of covariant version of this derivative
Yes.
operators. I didn't write it down here. You would have a square of the links before and after, and here just the link before and after this matrix to have this covariant parallel transport, the transport on the lattice.
Yeah, how big are N and L in practice?
Yeah, I mean, this is already here with the range of lattices that have been considered here. So usually you see that these kind of points you have rather large errors. So these can go up to 64, or I mean, they're even 128 or something like that. But
For L?
For the lattice extent, yeah.
And what about N?
So N so N here in this most precise data is around 16, but there are studies where it goes to 64 and.
Yeah, the reason I ask is that since I have a lot of friends in NVIDIA, nodes are getting fatter and fatter, more and more GPUs together, unified memory so that you can program as if it's one computer. And so I would avoid parallelization altogether, except for inside a node.
Yeah, I mean,
because you've got enough space there, and you probably, the technology will increase faster than your greed, right?
This
and
is
the other thing is there are more dense, beautiful, efficient, dense matrix routines that you can call in libraries on GPU than you can shake Vista. The only thing I would worry about, and I'm curious, is they often neglect complex arithmetic. So, but the other thing is they're really interested in lattice gauge theory. You can actually go in there and ask them to improve the libraries. So
yeah, I mean, I once was in contact with Kate Clark.
Yeah, right. Kate Clark is the one to be in contact to start with.
But unfortunately, she was focused on other things. But I've implemented a GPU version of this, and I've tried several aspects of to get this as fast as possible. The problem is, of course, you also, for the GPU, you want, it's better to have something that is better parallelizable and has less interaction. But of course, you can call all these kind of routines. I've checked
but
this.
I think it's even Kate would agree that as we go forward, this is going to become a huge set of libraries, probably callable by Python and all kinds of things. So, and their nodes are getting so fast that I would have, in a sense, what Exascale is doing is building good nodes and bad networks.
Yeah, I mean, this was
So-
the idea to go to this GPU code, which is not parallel, but instead it has a GPU.
Well, but it is parallel because they have libraries that do the
Yes.
GPU.
Yes, internal. I mean, it acts. It is not parallel on MPI.
Anyway, I would put your money on the 32 node GPU, 32 GPU box, 64 GPU box,
Okay.
unified memory. See, all of this stuff is coming down the pike, okay? And so I think that that is such a huge advantage in simplicity because they want to get this market, not yours, but everyone that has complicated codes. And so I think that that's got so much space and coming so fast that
Yeah,
for this
that's-
size of problem, that's where you should go.
Yeah, that's correct. But yeah, I'm wondering whether, of course, I think this GPU implementation that I've done, I tried various things, but I think there is still room for improvement in this respect. And I would be curious to contact also Kate and get more information of what she thinks about this. But
I'll try to convince her or other people there to take this.
Okay.
I mean, they care about this. If you do something that you say is quantum gravity, they'll put it on their webpage, okay? So,
Okay.
you know, right.
Okay.
Yeah, I just wanted to comment as well on the lattice, on the phase. We checked with several things, and it's quite lattice dependent. It's small in most cases. The additional gamma one that we use is an order of magnitude smaller for the lattice phase, but it's still
Which
it's
gamma?
tiny. This is in unpublished work. We've just
Okay. So you say that there can be phases where this becomes much smaller.
not in this model, no.
Oh,
It's actually it's small in all of the in all of the simulation, but it varies significantly with the lattice
Okay.
simulation. So one should be careful with it in a given simulation and given discretization. The ones that you described, it's fine.
Yeah, I mean it's definitely a problem because usually this is very expensive to calculate, and therefore it's not even monitored in a lot of simulations. So you just assume that it stays close to 1, but you're right. It could be that you hit a certain phase where it then really has to enter.
It seems not to be a problem, I think.
I just wanted to say that, of course, for matrix multiplication, GPUs work beautifully, and you can get one order of magnitude improvement, but it depends very much on the size, because if the size is too small, then you don't gain anything. So it could be worse. So and another thing is that it has to implement exactly the same code in each of these cores that are inside the GPU. So if so it's in this case, well, you have to work that out. Maybe the NVIDIA people can do it.
Yeah, the problem is that it's again a kind of parallelism that you have to introduce. So you have to run simultaneously a lot of small tasks, and this
but no
is
doubt
again a
that
problem.
GPUs are certainly a very good, very useful device for these kind of things. Yes.
I think that does it for this discussion. Let's thank Georg.